Good morning students. This is lecture 35 under module 12 and under this lecture today we will discuss about gas liquid and liquid liquid contactors. Basically the different types of contactors that are available for the membrane separation applications. Then we will learn about membrane reactor and bioreactor, and in a nutshell we will discuss about the PM hydrogen fuel cell, where membrane plays a very vital role. So, if we talk about membrane contactors, so the membrane systems mainly used to contact two phases to promote the mass transfer between them. So, it is a new way to accomplish separation like gas separation and liquid liquid extraction. The specific driving force through the membrane accomplishes the separation of compounds from one phase to the other opposite side. So, you have gas liquid and liquid liquid mass transfer, both can be achieved without dispersion of one phase within another phase. So, two phases are being separated by membrane. So, you can see there is the three types of membrane contactors, that is I have shown it here. The first is gas liquid contactor. So, basically one phase is gas, another phase is liquid, and in between there is a membrane. This is your membrane. So, then second one is gas liquid contactor. So, here the liquid phase is in the upstream side and gas is in the opposite side, and this is just the reverse of the first one. That means the two different phases have changed the sides. And then we have a liquid liquid contactor in which both the phases are liquid and being separated this one by a membrane. If you talk about the principle, then gas liquid and liquid mass transfer without dispersion of one phase within another is usually accomplished by passing the fluids on opposite sides of a microporous membrane. So, careful control of the pressure difference between both fluids is necessary to immobilize one of the phases in the pores of the membrane. The fluid interface is located at the mouth of each pore. So, basically this you can see the fluid interface. Okay, so, this is the pore mouth, right. The main role of the membrane is to act as a barrier and to increase the surface of mass transfer exchange between both the phases. So, the common feature in these processes is that the separation performance is determined by the distribution coefficient of a component in two phases, which component basically or which solute you want to separate, what is its distribution coefficient in both the phases, that plays the big role in deciding how the solute will be transported, apart from other governing factors. So, generally it is the large area per volume that makes the process more attractive rather than the enhanced mass transfer. So, the transport mechanism, let us understand how this is happening. So, a component I is transport from phase 1 to phase 2 using 3 steps. So, first is of course, the transfer from phase 1 to the membrane, then diffusion through the membrane. So, I can just trying to draw. So, let us say this is the membrane. Okay. So, this is here let us say phase 1, this is your phase 2. Okay. So, let us say this component which is present in the bulk okay, is to be transported to the other side of the phase, other side of the membrane, that is permeate side, okay. And this is your membrane, right. So, what will happen? So, it will first move from the bulk and will come to the surface of the membrane. So, it will then sit on the surface membrane, right, then it will diffuse through the membrane. Once it diffuses through the membrane, it reaches the permeate side, then it dissociates itself from the membrane completely or detach itself and then comes to the permeate side. Okay. So, the flux of I can be re-expressed as Ji is KOVI into delta Ci. Here KOVI is the overall mass transfer coefficient. This also we have learned, but just repeating once again for your fast understanding, that 1 over k OVI, which is the overall mass transfer coefficient, can be expressed in such a form which is the combination of the mass transfer coefficient of 3 factors. So, k of feed, k of membrane and k of the receiving phase, that is the permeate phase, that side. So, in case of mass transfer resistance remain completely in the membrane phase. Okay. So, you can write that Ji equals to di Ki by L delta Ci or Pi by L delta Ci. So, where K is the distribution coefficient of the component I from the phase 1 to the membrane phase, and di is the diffusion coefficient of the component I in the membrane, and delta Ci is the bulk concentration difference, L be the thickness of the membrane. So, advantages are, so high contact area, 30 times more area than what what is achievable in gas absorbers, and 500 times what is obtainable in liquid extraction columns. Physically separates the counter flowing phases. The membrane area between them is independent of their relative flow areas. So, large flow ratio differences can be used without producing operating difficulties. Now, flexibility, that is means independent control of fluid flow rates. So, there is no emulsions, there is no question of any flooding at high flow rates, which is actually a problem in packed column towers, even distillation towers also. No unloading at low flow rates, there is no density difference between the liquids that needs to be considered, no drop dragging of liquid phases. So, you can say this is more a very easy to operate type of system, and controlled and known high interfacial area, linear scale up, and compact and less energy consuming. However, it has certain disadvantages also. It requires an additional phase, which is here membrane, and the membrane phase contributes to the overall mass transfer resistance depending on the type of the membrane and the system used. System instability may occur, such as when the applied pressure exceeds the wetting pressure, liquid penetration may occur inside the pores. So, this is another problem. So, pressure has to be controlled very efficiently. Slow dissolution and emulsion formation may remove the membrane phase in case of two liquid phases. When we are talking about two liquid phases, if one is a gas phase, another is a liquid phase, then it is fine. But when there are two liquid phases, then if they are mixing and forming some emulsions, then it may create another or an additional problem. So, commercial membrane contactors are this one basically they are manufactured by so many different companies, just listed one or two here. So, a Membrana Charlotte company in United States is a leading manufacturer of membrane contactors. So, membrane modules of various performance designed for mass transfer tasks in gas liquid systems are available. The commercial membrane contactor Liquicell is equipped with porous polypropylene membrane cell guard X50, which are supplied in a fibermat format. You can see how this looks like actually. Okay. So, this is a gas liquid hollow fiber membrane contactor for different applications. Okay. You can see this liquid will go here and liquid will out here, and so your vacuum gas or sweep gas will come here, okay, or it will be out here, right. So, this is you can see how the distribution of tubes inside, and these whatever you are seeing these lines here. So, they are actually hollow fiber membranes, right. There are baffles inside to help in distribution of the liquid inside that, and there is a collection tube in between which you are seeing, in which your liquid will be collected. This is how the assembly looks like, actually hollow fiber assembly. This is a single hollow fiber membrane, and this is how membrane pores are in detail. This is an SEM image. Okay. So, you just get an idea basically about how these things happens. So, the design allows simple packing of membranes into commercial Liquicell contactor housings. A membrane sheet is wound around the axial porous tube, and the membranes are parallel to the tube axis. Anyway, these things we have discussed during our membrane modules and all, but just quickly going through it will this one, so that you can recollect the things quickly. So, the baffle located in the middle of the axial tube and module bisects the module and directs the liquid into fiber cell in the first compartment of the module. Just let us quickly go through the different types of materials that is being used for the membrane, though we have discussed it in detail. Polysulfone, polyether sulfone, polyether ether ketone, then polyethyramide PEI. It is gaining a lot of interest nowadays in this particular membrane. Otherwise, mostly commercial membranes you will see that they are polysulfone or polyether sulfone or PVDF or PTFE. So, then polyethylene, polypropylene, PVDF, PTFE polytetrafluoroethylene, PMP, then PDMS. Okay. So, these are some of the materials that are being used for the preparation of the membranes. So, let us now discuss little more detail about the contactors. So, let us first understand about the gas liquid contactor. So, here one phase is a gas or vapor and the other phase is a liquid. So, the gas or vapor can be transferred from the gas phase to the liquid phase, or the gas or vapor can be transferred from the liquid to the gas phase. Either way you can operate it. So, if you do it like this, that the gas is transferred from the gas phase to the liquid phase. So, this is how it happens actually. Okay. And here it is just the reverse of that, the gas is transferred from the liquid phase to the gas phase. Okay. So, usually porous membranes are used in this such type of contactors. The membrane act as a barrier between the two phases. Two scenario can be possible. The first, pores filled with the gas phase, second, pores filled with the liquid phase. So, this is the schematic is showing about how it happens. So, here you can say the pores are, these are the pores. Okay. So, these are filled with the gas phase. Here you can see the same pores, these are filled with the liquid phase. So, pores filled with the gas phase usually occur in case of a hydrophobic membrane. To achieve that, the first case where the pores are filled with gas phase, we need a hydrophobic membrane. So, as for example, polytetrafluoroethylene, polyethylene, etc., with a liquid phase which is basically a aqueous solution. The membrane pores are filled with gas phase, as the liquid phase do not wet the membrane. So, you have to choose the membrane material in such a way, that is why hydrophobic material. The mass transfer resistance is normally located in the liquid phase. So, this is the concentration profile, how it happens. This is your membrane, okay. The gas phase, then liquid phase, and this is the gas phase boundary layer, this is the liquid phase boundary layer, okay. Upstream, this is upstream side, this is downstream side. Okay. So, in the second case, which are pores filled with liquid membrane. So, to achieve that, we need a hydrophilic membrane, just the reverse of the hydrophobic one, with a liquid phase, obviously that is aqueous solution. So, the liquid phase here wets the membrane. Okay. In the earlier case, the liquid phase is not wetting the membrane. So, the mass transfer resistance is again normally located in the liquid phase. So, you can see the same thing here, gas phase, this is liquid phase, this is membrane, this is gas phase boundary layer, this is liquid phase boundary layer. Okay. Then the next one is liquid-liquid contactor. So, here both the phases are liquid, separated by a porous or non-porous membrane. Now, for a porous membrane, the feed phase may wet or not wet the membrane depending upon the nature of the liquid. So, let us understand different cases. Let us take the first case, which is hydrophobic porous membrane, okay, with organic solvent as feed and aqueous phases permeate. So, you can see how it looks like the schematic diagram. Here liquid or phase here, another liquid phase here. So, let us say phase 1, phase 2. So, this is feed side, this is permeate side, this is the porous membrane. Here the membrane contactor with a wettable liquid feed phase, actually the membrane, the liquid phase which is in the feed side, it is wetting the membrane basically. So, the feed wet the membrane and fills the pores. So, feed side or liquid is being filled here, you can see the dotted here. So, all the pores are filled with the feed phase liquid, because that liquid is wetting the membrane. Then the aqueous phase on the permeate side does not wet the membrane. So, liquid-liquid extraction occurs in the interface between the two solvent formed at the permeate membrane side. So, most of the mass transfer resistance remain in the boundary layer and the permeate side. Okay. So, here only most of the mass transfer resistance is located, and mass transfer resistance in each three phases must be calculated to obtain the overall mass transfer resistance, and of course, to find out that which is dominating. So, it has been seen that the mass transfer resistance in the boundary layer of the permeate side, that means this one, okay, is the dominant one. Then the case 2, here hydrophobic porous membrane with aqueous phase as a feed and organic solvent as a permeate, right. So, here you can see the feed phase is a aqueous phase liquid, again it is liquid basically, but in the permeate side it is a organic solvent instead of a aqueous solvent. So, organic solvent or permeate side will wet the membrane. So, organic this one will wet the membrane. So, you can see now the pores are filled from the permeate side liquid, okay, and the interface will form a feed, the interface will come here it will be basically, that is the feed and membrane side. Most of the mass transfer resistance remain in the boundary layer at the permeate side. So, again the mass transfer resistance will be here. So, just quickly we will go through certain applications. So, recovery of valuable aromatics fractions from the food industry's wastewaters. So, a synthetic, let us say a synthetic aqueous solution which was used as a model industrial wastewater flowed inside to a fiber lumen, hollow fiber lumen. So, the solvent phase that is being used is anhexen flow on the cell side of the module. Okay. So, tube side and cell side, let us say this is the tube side, then we have a cell side. Okay, something like this, right. So, you can just extend it little more here to understand. Okay. So, something is here and something is here. Okay. So, this is we can say the n-hexane. Okay. So, this is your feed. So, both the phases are totally recycled into their own feed reservoirs. So, both phases are regularly sampled at the bypasses and analyzed by gas chromatography in order to monitor the mass transfer. So, this is a more better complete schematic diagram. So, you can see that this is a pilot scale extraction device here, the feed phase reservoir, this is feed phase reservoir, this is your solvent phase reservoir which is n-hexane, this is your hollow fiber module, then there are different pumps, bypass valves and sampling points. Okay. Since I told just in the earlier slide that both the feed as well as your solvent which is being used passing through the membrane are totally recyclable. So, this system operates in a total recycle mode. So, another application is purification of biodiesel. So, the use of biodiesel in engine requires a high purity, almost 99.65 weight percent. So, membrane extraction can be considered as a more efficient and environmental friendly process to purify a synthetic biodiesel stream composed of methyl esters from rapeseed oil, methanol and glycerol. So, the feed, biodiesel stream and extractant water are pumped by an air motor gear pump. Membrane module made up of two semi cells in PTFE material is used. The extractions are performed using a module in a co-current configuration, so that constant pressure difference across the module is maintained. The feed tank and the water tank are used to keep the system diluted during the experiments. Both phases are recycled into their respective reservoirs. The concentration of the methanol and glycerol can be measured in a GC and HPLC respectively to monitor the mass transfer. So, let us see the schematic diagram here. So, this is the experimental setup in a co-current configuration. So, this is your feed vessel, this is your extraction vessel, this is your membrane. Okay. Then there are different types of bypass valves, pumps, regulating valves, flow indicators. Okay. So, and manometers in the inlet and outlet of the membrane cell. So, another application is ammonia removal from industrial wastewater streams. So, the ammonia aqueous solution is passed through the lumen side and the stripping solution containing sulfuric acid is pumped into the cell side of the HFMC hollow fiber membrane contactor. Okay. And both solutions are recycled to their own reservoirs. The reaction between ammonia and ammonium and sulfuric acid is very exothermic. So, a cooling water system is used to prevent increasing the feed temperature. The concentration of ammonia is determined at regular interval to know the mass transfer. So, it is a very simple schematic of this separation actually for ammonia stripping. So, here you can see the feed resolution. So, there is a cooling is provided because it is exothermic reaction happens. So, you pump it and a hollow fiber membrane system, okay, HFMC. So, then the stripping, so this is the stripping solution, whatever is coming out, okay, here after passing through it is mostly retented. So, again being recycled to the feed tank. Okay. So, another application is membrane gas absorption technology for carbon dioxide separation. So, you know it combines membrane separation and chemical absorption technologies. Separation role is fulfilled by the use of a absorption liquid. For ideal solution, all the pores of a membrane are completely filled by gas in order to minimize mass transfer resistance. So, this is a carbon dioxide membrane gas absorption principle. What is happening? You say this is solvent here, this is flue gas inlet which is having carbon dioxide. Okay. So, you can see that this is the how the carbon dioxide is going like this. This is your liquid gas interface here. Okay. Here the liquid gas interface, the carbon dioxide is passing through the membrane pores and then getting absorbed in the solvent or absorption liquid which is present on the upstream side. So, in a result, the reactive absorption liquids in these systems are preferably physically reactive liquids because of their higher absorption rate and capacity. So, the advantages are, so it requires less size than the conventional absorption towers, operational flexibility is there, easy to maintain basically and easy to operate. The rate of mass transfer is very high and as you know the scale up is linear. So, another application is biogas purification. So, biogas or you can call a gobar gas. So, a gas mixture of 60% methane and 40% carbon dioxide. So, which is in the composition range of biogas is fed into the tube side of a liquid gas membrane contactor module. So, whatever being reported here actually, so this is simulated biogas basically. So, deionized water and MEA absorbents are circulated through the cell side. A peristaltic pump is used to deliver the liquid from the rich storage tank through a rotameter to the membrane contactor. A gas chromatograph was used to analyze the inlet outlet concentrations of methane and carbon dioxide. To precipitate absorbed carbon dioxide as barium carbonate, excess amount of 10 % of barium chloride solution is added to the aforementioned solution. And this is the schematic representation. So, you see the carbon dioxide methane mixed gas is being fed to the membrane system, which is fitted with a PVDF hollow fiber membranes. Okay. Then you can see this the lean storage tank, the feed is coming here, okay, and then whatever it is coming out in the permeate side is being collected here, okay, and some of the pressure this one gas after removing it is going through this one, then you can collect here and you can measure of course through the GC or HPLC system to find out the concentrations of both carbon dioxide and methane. It is a very simple operation actually. Another application is dissolved oxygen removal from water. So, this is a very important application in industry, industries such as pharmaceutical, food, power and semiconductor. So, you need to remove the dissolved oxygen from water. Removal of dissolved oxygen from water requires driving force for transmembrane transport. Thus, it is required to have a reduced oxygen content in the gas phase. So, different approaches are used. So, you can have a vacuumized operation. So, you can use a sweep gas or which is called the sweep gas based operation, or you can use both vacuum and sweep together. So, in the vacuum only operation, the best separation is achieved when vacuum is applied from both ends. So, all dissolved gases can be removed at the same time with a high degree of separation by applying a very deep vacuum level. So, in a you can see how it is happening actually. So, this is the vacuum operation, the membrane, liquid is entering here, liquid is out here, and now you are vacuumized the entire system here, something very similar to pervaporation type of operation. Sweep gas again here, liquid in, liquid out, and we are sweep gas in and sweep gas out. Okay. So, during the sweep gas operation, it employs a inert sweet gas such as nitrogen or argon to remove the target species. Here the target species is our oxygen. So, it is an efficient process, but tends to saturate the water with sweep gas. Okay. And then combination of both vacuum and sweep operation, you can see here, this is how it is happening here. So, it is a combination of both vacuum and sweep. So, liquid in, liquid out, sweep gas in, and it goes to thus whatever sweep gas is being out, it is vacuumized, right. So, here and allows a high degree of separation with a less sweep gas and still maintains low levels of dissolved gases in the product water. So, now let us discuss little about membrane reactors, then we will of course talk about membrane bioreactors also. So, the what is concept of membrane reactor is that, so it is an apparatus that integrates a chemical reaction and a membrane based separation. Basically, in a single unit the chemical reaction is happening and as well as within the presence of membrane the separation is happening. So, you see how it happens in the schematic diagram. So, the membrane acts as the separator and also the reaction vessel where the reaction occurs. One of the end product is removed to shift the reaction towards high conversion and of course, to increase the final product concentration. So, let us say A is giving B plus C. Okay. So, this is a schematic diagram of a membrane reactor where a mixed feed of A and B enters the membrane. Okay. Then C is produced in the reactor and B diffuses out through the membrane pores. So, there are multiple ceramic membranes, these are ceramic membrane systems, okay. But only two are shown here for the simplicity purposes, and you can see that B is diffusing out through the membrane pores, right, and then you get C is the product. So, for the reaction A and B to happen, two concept can be arises. So, either reaction and separation can be combined in the one unit. So, where it is usually used in combination with inorganic membranes and polymeric membrane with a catalyst coupled with it, and otherwise you can have a reaction and separation are not combined and the reactants are recycled through a membrane system. So, here it is usually applied for any membrane process with organic or inorganic membrane. Okay. So, here you can see how it happens. So, if you are talking about a single unit, so this is something like that, simplest one, right. So, here the reaction separation is happening in the single unit. Here in this case we have a separate reaction unit which is reactor where the reaction is happening, then the product stream goes here. So, here is a membrane unit, okay. Here we are getting our let us say the product B, okay, and whatever unreacted A is there left out. So, here, okay, it is again recycled back to the reactor. So, reaction is reaction and separation are happening in the different units. A membrane and catalyst configuration, since we talked about catalysts are required to enhance the rate of reaction. So, we can have different types of arrangements. So, the first arrangement is that catalyst located inside the bore of the tube. Bore of the tube means the membrane tube. Okay. So, most simple and straightforward system. You can see how it happens here actually. So, the feed, so if you see the bore, this is how it looks actually. So, bore with the, these are catalyst, bore with the catalyst, and this is your membrane. This is your membrane phase, right. And inside that hollow fiber you can see inside of the string. So, let us say this is a single hollow fiber, okay. So, this total area, okay, this is filled with your catalyst, okay, in a packed bed type of system, something like that you can just assume. So, it is a very it is a very simple and straightforward system. So, it is very simple to prepare and operate. So, new catalyst can be easily introduced by replacing the poisoned catalyst. So, you can just remove the poison catalyst because it is just packed inside this one, no permanent attachment. Okay. So, your feed is entering and directly coming in contact with the catalyst, whatever the reaction is happening, and if you are having a purge or sweep gas outside the lumen, okay, of the membrane. So, that helps us in the rate of enhanced rate of mass transfer. So, your product retentate is coming here and other things can come out like this. So, another thing is that catalyst can be immobilized on the top of the membrane or in the membrane wall. So, here the membrane wall is immobilized with catalyst. So, this is bore is now completely empty. The membrane itself is the membrane area, whatever the membrane. So, that is impregnated with the catalyst. So, one of the product, not necessarily the required product, should permeate across the membrane. So, that you decide actually by virtue of the nature of the reaction, what type of reaction will happen. So, one will diffuses out something like this through the membrane. Okay. So, this is another one where the top layer is loaded with the catalyst. So, you can see how it is happening here. So, the not the entire membrane, but the top layer only, top portion of the membrane itself is only loaded with the this one, and the bore is remained. So, the area which is inside the bore basically. So, that is being, you can see the schematic how it looks like. Okay. So, the feed is entering here and the retentate is getting here. Okay. So, you can get some product from here, okay, through the membrane. So, of course, you use perm selective membranes. Let us understand few applications quickly. So, catalytic membrane reactor for the production of biofuels. So, the catalyst is pressed inside the aluminum membrane, assuring that its location coincides with that of the palladium and silver layer. So, in this case, particular case, okay, which was taken from this particular actually reference. So, you can see that the configuration and is done in such a way that hydrogen will permeate through the outer layer of the membrane, okay, and is distributed among the catalytic area in the reactor. You can see these are the catalyst area inside the reactor, okay, through which hydrogen is coming here. Then hydrogen and carbon monoxide. So, you will get the your products here, okay. And basically the outer one is made up of stainless steel, there are gaskets to hold it, and this is inside this is the this one basically. So, this is your palladium silver membrane. So, hydrogen permeation through this membrane is measured by flowing hydrogen and carbon monoxide through the retentate and permeate sides of the membrane respectively. So, another application is catalytic membrane reactor for dehydrogenation. So, the reaction is carried out isothermally in a membrane reactor with no pressure drop. You can see the reaction how C6H12 is getting converted to C6H6 plus 3 hydrogen. So, since the membrane is chosen in such a way that it is permeable to hydrogen, so hydrogen diffuses through the membrane and you get here pure C6H6 here. Of course, there is a sweep gas you can see here that is flowing, that helps in enhancing the rate of mass transfer also. So, a sustainable hydrogen production from ethanol and water. So, water splitting reaction that takes place at the tube side of the membrane, and the oxidative steam reforming of the ethanol occurs on the cell side simultaneously. Two reactions are happening, one is this water splitting reaction, another was here ethanol steam reforming reaction. So, you see the ethanol plus 2 water plus half oxygen is giving us 2 carbon dioxide plus 5 hydrogen. So, more clearly ethanol and water react with oxygen, which permeates through the membrane upon water dissociation to produce hydrogen and carbon dioxide over supported transition metal catalysts. So, you can see how it is happening. This is your membrane and this is your cell side, right. So, in the cell side we are passing methanol plus water, sorry, ethanol plus water. Water is only being passed through your lumen side, and that is the water splitting reaction is happening where we get hydrogen here and we get carbon dioxide and hydrogen here. Now, let us discuss little about membrane bioreactor. So, you know membrane bioreactor is a device where a perm selective membrane is used, such as a microfiltration or ultrafiltration that is integrated with a biological process. So, in a membrane reactor it is the chemical reaction that is happening and separation that is happening inside the membrane module, and here in the reactor bioreactor it is coupled with a the membrane contactor is basically coupled with a biological processes. So, widely used for municipal and industrial wastewater treatment. Almost all commercial membrane bioreactor processes use the membrane as a filter that reject the solid materials developed by the biological processes and produce a clarified and disinfected product effluent. So, membranes have been extensively used as a support for biocatalyst. So, that is those are enzymes or whole cells immobilization with the aim of implementing membrane bioreactor. So, this is a schematic representation of the membrane MBR process. You can see the bioreactor here, the cells are there may be extracellular enzymes, other biocatalyst also. So, the membrane is helping to retain them everything on the side where the biological reaction is happening. And whatever it is unwanted, it will pass through the membrane. So, you will get basically solids and microorganisms that are retained, and clean water is coming to the permeate side. If you compare its membrane bioreactor advantage to the traditional ASP, the activated sludge systems, okay, ponds. So, the quality of effluent is far better and superior, and the consumption of energy requirement is very low because you are dealing with a membrane system. You know membrane system consumes very low energy. It is simple and stable because of the membrane integration, and since you are integrating membrane in between, so you do not know very huge pond size. So, the plant area requirement becomes less, of course, with a reduced operational cost, higher volumetric loading rates, and the best two things are these, that shorter hydraulic retention time. HRT is very small and longer solid retention time. SRT is very high. This is what actually we need in biological systems, less sludge production than that of the activated sludge process, and its potential for simultaneous nitrification denitrification in case of long SRTs. However, it has some disadvantage. The most important disadvantage is the membrane fouling. So, the fouling of the membrane significantly reduces the membrane performance and membrane lifespan. Fouling is mostly due to the suspended particulates, which are microorganisms and cell debris, colloids, solutes and sludge flux. So, these materials deposit on the membrane surface as well as in the pores, thereby clogging pores, which leads to a decline in the permeability of the membrane. The heterogeneous nature of suspended solids and active microorganisms in mixed liquor suspended solid, that is MLSS, makes membrane fouling an inevitable challenge that is difficult to control in long term MBR applications. Now, we will just see how this is happening, this fouling business actually. So, this is the mechanism of membrane fouling in membrane bioreactors. You can see this is the new membrane, no fouling. So, you will get the cleanest of water, the flux will be very good. Just the operation started continuing, you see that pore narrowing started. That means, the particles started getting deposited inside the pores. Okay, and the solids are started depositing on the membrane surface, thereby in the form of flux. Okay. Then pore clogging is coming here. You see the flux coming and sitting on that mouth of the pore. So, this is called pore clogging. Then you can see the cake formation, okay, or gel formation, whatever you can say. Now, this is complete fouling mechanism, and a very nice picture it has been depicted how fouling actually happening in case of membrane bioreactors. So, these are the factors that affect the membrane fouling in membrane bioreactors. Okay, membrane characteristics. So, as a material type, what is the water affinity, what is their water affinity, of course, surface roughness, surface charge and pore size. Then operating conditions such as operating mode, rate of aeration, SRT, HRT, F by M ratio, OLR, COD by nitrogen ratio, temperature if at all is there. Then feed and biomass characteristics, the MLSS, then sludge apparent viscosity, EPS, what is the flux size, alkalinity and pH and salinity. All of this, so you can understand there are so many different parameters that affect the membrane fouling in case of MBRs. So, how do you abate it, how do you reduce it basically, though you cannot do away with, you can reduce it, minimize it. So, there are few techniques suggested by various researchers to overcome the MBR fouling problem. The first is addition of coagulant, which is very popular. The another one is addition of adsorbent, mostly the similar procedure, but the two different material. The one is coagulant and the one is adsorbent. And then you have use of granular biomass, basically the aerobic granulation, and then you can have granular material with aeration and quorum quenching. We will just quickly go through one or two of these things. So, what the coagulants is doing? So, coagulants help the formation of large size sludge flux. Why you want to do it? Because if the sizes are small, they will try to penetrate through the membrane pores. So, we do not want that, right. So, if the more bigger the particle sizes, the flux sizes become very big, they will just sit on the membrane surface, they will not push themselves to the membrane pores. So, alum and ferric chloride are very good coagulants. They are reported to enhance the filterability of MBR mixed liquor and ultimately control the membrane fouling. So, and then you can add adsorbents also, you know adsorbents AD. So, they have a very large surface area for the adsorbent of materials in water and wastewater. What they are adsorbing basically depending upon the charge based interaction of the component that wants to be adsorbed on the surface of the adsorbents. So, that basically they are adsorbing dissolved organic polymers, thereby reducing membrane fouling propensity. So, powdered activated carbon can be used because their surface area is far higher than that of the granular activated carbon to reduce organic fouling and biofouling, but the problem with powder activated carbon is to get rid of it or filter it, basically take it out is a problem. So, there many times you use granular activated carbon, which is known as GAC. So, PAC helps in bacterial attachment and subsequent growth. Once they do it, okay, then the sizes of the PAC becomes bigger, so that it is easy to retain on the surface of the membrane, right. So, what is aerobic granulation? Aerobic granulation refers to the process of microbe to microbe self immobilization without any biocarriers. There are no biocarriers here. So, the resulting granular biomass are dense microbial consortia packed with different microbial species that can collectively degrade wastewater pollutants. So, compared to the ASP, aerobic granulation technology offers the following advantages. It has excellent settling properties, smaller footprint, a strong microbial structure, higher biomass retention, less sludge production, high resilience to toxic chemicals and good ability to handle high organic and shock loading rates. So, this is all about how you can reduce the MBR fouling, basically fouling in the membrane bioreactors. So, the applications, there are many applications. The most and foremost important application is of course wastewater treatment. So, the bioreactor is a vessel in which the chemical process is carried out, which involves organisms or biochemically active substances derived from such organisms. Okay. So, this is an aeration system, filtration system you can see here. So, and membrane filtration in terms of tubular systems you can have, or you can different types of membrane contactors can be used, HFMC can be used, plate and frame type also can be used. Okay. So, the process can be aerobic or anaerobic, it does not matter, both can be fine for the membrane bioreactors. So, they are commonly cylindrical, ranging in size from liters to cubic meters and are often made up of stainless steel. So, you can use either this type of hollow fiber, these are HFMC systems, membrane contactors. Okay. So, you can otherwise use plate and frame type modules, okay. Something like this, they are hanged in your activated sludge ponds. Okay. So, this is also possible. It is easy to do, you can take out one, wash it, again put it back, right. Then another application is methane fermentation. So, here raw materials, basically distillation residue or food waste, are fed into the system. The residues are stocked in a solubilization tank for a few days to let them solubilize, basically stabilize. So, the solubilization tank performs the equalization of nutrients and storage of the raw feed. So, after that, after few days, so the liquors are introduced into the methane fermentation tank, where thermophilic digestion takes place. Now, the MF tank has a subcompartment called submerged membrane specific separation tank, the SMS tank, okay, where the submerged membrane units are installed. The anaerobic sludge is concentrated at the SMS tank, then recirculated to the MF or pumped to the sludge treatment line. The biogas generator consists of 60% methane, 40% carbon dioxide, and a few minor components such as hydrogen sulfide. So, this is the schematic. This is Kubota, is a company which makes this famous anaerobic membrane biological reactors known as KSAMBR. So, you can see the pre-treatment equipment here, okay, the distillation reduction and getting equalized here in a solubilization tank. After that, it fed to a high temperature, high speed methane fermentation tank, where the methane is getting formed, right. Then it goes to the submerged membrane type of system here. So, it is a tank in which the membrane module is being submerged, okay, in a aqueous system or form. So, then you get the wastewater treatment equipment, it goes to the whatever it is coming from the membrane system goes to the wastewater treatment equipment, right, and from the sludge also comes whatever from the methane fermentation tank, sludge dehydration equipment, right. Then the biogas which is forming here is go for power generation facility, boiler, etc. Okay. So, this is an excellent system, it is in place in many installation around the globe and is found to be one of the best or efficient systems. So, the next or the last which we are going to discuss in today's class is about PM hydrogen fuel cell. You know, fuel cells are gaining a lot of importance since few decades. Almost it was first fuel cell was actually PM fuel cell was actually designed by General Electric for one of the NASA's spacecraft known as Gemini in 1960s, long back. Okay. So, a PM means proton exchange membrane cell uses hydrogen and oxygen as fuel. So, the products of reaction in the cell are water, electricity and heat. So, PMFC is a big improvement over internal combustion engines, coal burning power plants and nuclear power plants, all of which produce harmful byproducts. The only bottleneck in PMFC that we do not have a very large size PMFC that can be fabricated and can be designed. So, these are very small units, you can up to a decent size you can make, but you cannot have other, you cannot just like that, the scale cannot be compared with that of the power generation due to by IC engines or thermal power plants or hydropower, something like that. You can see how it looks like actually. So, the fuel in here, right, the excess fuel that goes out here, basically hydrogen then permeates to the anode, okay. So, it comes in contact with the anode and it generates the electrons, then it passes through this is your PEM, proton exchange membrane, right. It is exchanging only the protons, it is a semi permeable membrane, it exchanges only protons, nothing else, right. So, the proton gets passes or diffuses through the membrane and then reaches to the cathode side, where it gets converted to water, okay. And by virtue of the electron transfer, electricity is getting generated here, right, and you can harvest it then. So, just let us quickly go through the different types, different components of this one. The first one is of course cathode. Okay. So, cathode, this is the cathode. Okay. You can see this is the cathode. So, this is the positive part of the fuel cell or post of the fuel cell. It has channels etched into it that distribute the oxygen to the surface of the catalyst. So, it also conducts the electrons back from the external circuit to the catalyst, where they can recombine with the hydrogen and oxygen to form water. So, this is the reaction that happens in the cathode. Oxygen plus 4 proton and plus 4 electron gives 2 of water. So, in the next one is anode. Okay. So, this is your anode here. right. So, it is the negative post of the fuel cell, it conducts the electrons that are freed from the hydrogen molecules, so that they can be used in an external circuit. So, it has channels etched into it that disperse the hydrogen gas equally over the surface of the catalyst. The reaction that happens at anode is 2 hydrogen is gives proton plus 4 electrons. So, the overall reaction is 2 hydrogen plus oxygen gives 2 water. The next one is PM, the membrane itself. So, this is the proton exchange membrane, also known as polymer electrolyte membrane. So, it is many times people call it electrolyte. So, it is a semi-permeable membrane generally made from ionomers and designed to conduct protons while acting as an electronic insulator and reactant barrier, as for example to oxygen and hydrogen gas. So, for a PFMC, the membrane must be hydrated in order to function and remain stable. So, the protons pass through the membrane to the cathode side of the cell, while the electrons travel in an electrical circuit generating the electrical output of the cell. So, it is a very simple operation, and the another one thing that catalyst, the unit catalyst. So, it is a special material that facilitates the reaction of oxygen and hydrogen. It is usually made up of platinum nanoparticles very thinly coated onto the carbon paper or cloth. The catalyst is tough, rough and porous, so that the maximum surface area for platinum can be exposed to the hydrogen and oxygen. The platinum coated side of the catalyst faces the PEM. Okay. So, you can we have seen how this operates actually. This is schematic representation. Okay. So, there is a anode here, there is a cathode here, the pink color is the membrane, PM membrane. Okay. So, hydrogen is coming here and air or oxygen is flowing here. So, oxygen flow field you can see here. Okay. So, this is all about your PM fuel cell. So, just quickly go through the advantages. The more efficient than combustion engines, no doubt about it, but in a bulk or a large scale it is difficult to do. So, low operating temperature, quick startup, direct emissions from a fuel cell vehicle are just water and a little heat and avoid greenhouse gases. Fuel cells have no moving parts. So, that is another advantage in during operation. However, it has certain disadvantage and also the cost of material is very high. The membrane itself has a huge cost and low, the density of the power that will be generated is very low. So, you cannot just compare it with our other membrane separation other this one power generation systems, and so lifetime is very short, difficulty in management, dehydration at high temperature and oxygen leakage from cathode to anode. In that case the reaction will have a lot of problem. So, with this we conclude today's lecture. So, mostly it is taken from different books actually. So, partly from Mulder and B.K. Datta like this. Okay. So, please go through the lecture. So, in case you have any query, do feel free to write to me. So, thank you very much. You can write to me at kmohanty@iitg.ac.in. In the next class, which is going to be the last lecture of our this membranes course, that will be lecture 36, module 12. We will discuss about perstruction, membrane chromatography and controlled drug delivery. Thank you very much.